In the last video, we talked about the even power functions. Now let's talk about the odd power functions. So odd power functions, meaning they have odd degree. So just like before, where we did x squared, x to the fourth, and x to the sixth, this time we're going to do x cubed, x to the fifth, and x to the seventh. And if you want, remember you can go to desmos.com. I will put that right here again. And click at the top where it says Graphing Calculator. I think we've done this in class a couple times. And you can type in these so that you can see what they do. But for these, it's pretty much the same as with the even-powered ones. It's just the shape of the graph is different. The solid line is x cubed. The long dashes are x to the fifth, and the short dashes are x to the seventh. And we could get that by plotting points. I'm not going to do that on this one, but you could. So let us now go look at the same questions we answered for the even ones. So one thing I should note is all three of these graphs have the same point at -1, -1, 0, 0, and 1, 1. And that's going to be important because we're going to have to answer those questions. So let's scroll down. Do they share the same shape? Well, yes, they all look like our cubic Superman curves, right? Do they share any points? I just answered that. They all have -1, -1, sorry, 0, 0, and 1, 1. Are they symmetric to the y-axis, the x-axis, or the origin? Remember, y-axis means fold along the y-axis like we did with the even functions, and then the two parts match up. X-axis means if we fold it on the x-axis, the two parts match up. And origin symmetry means we have to fold on the y and the x-axis. So in this case, if we fold along the x-axis first, this right-hand part that's in quadrant 1 folds over the x-axis and is then in quadrant, quadrant 4. And then if we fold over the y-axis, it folds over this way and lines up perfectly. So the odd functions have origin symmetry. So let's scroll back down here. What's the domain of these? Well, they're still just polynomials, so it's all real numbers. The range of these, since they go as small as -infinity and as large as +infinity, the range is also all real numbers. And when we answer that question, it's pretty much the same as with the even ones. As n increases, the y values get closer to 0 as x gets closer to 0, but the y values get larger as x goes to infinity and smaller, meaning more negative, as x goes to negative infinity. So again, just to color coordinate here, this piece right in here, that's the part where x is getting close to 0. And as you can see, for the same values of x, the y's get closer to 0 as the exponent gets bigger. And then again, for the parts where we get to negative infinity, that is what I just highlighted in green. And those numbers get smaller faster, right? So like negative 2 to the 5th is much smaller. It's negative 32 as opposed to negative 2 cubed, which is only negative 8. And then where x goes to positive infinity, it's the reverse situation. Things get bigger faster when the exponent gets bigger. All right, so that covers functions of odd degree. In the next video, we'll look at using our transformations again to graph these.